a bunch of electrons and fit them in the same quantum state, every electron has to have its own. So do each of the quarks. Each of the quarks have to have their own quantum state. Now, if these are spin half particles, what would be the spin on a proton or a neutron? And there's rules for adding the spins of particles together.
Are these kind of like dipoles? So that's 3 of them?
Yeah, there's 3 spins. So it turns out that if I have spins of 1/2 and 1/2 and 1/2, what's the most spin I could get in any individual direction? I get all 3 objects spinning in the same orientation. The most I could get would be what? 3/2. What's the lowest number I could come up with? Yeah, what could be -3/2? I could orient them all in the other direction. So I could think of this as plus minus, plus minus, plus minus. Highest number I could get is 3/2. Lowest number I could get is -3/2. And then I can also get anything that is an integer step away from the 3/2. So for example, I could get a step below this would be what? 1/2, and I could get -1/2. So it says if I take these 3 quarks right here, 2 ups and a down, I'm not guaranteed that's a proton. There are different possibilities for 2 ups and a down. The proton is actually the particular state where the ups and the downs here combine their spins in a way where we get 1/2 unit of spin. Okay, so the proton is a plus half part, is a half particle. I shouldn't say plus half. S is equal to 1/2, so is the neutron.
Plus or minus?
They're not really plus or minus. This is the big S. M sub S. What would M sub S be? M sub S could be plus or minus. And I should, these are not M sub S values. They're relative orientations. So what we can do is ignore these states and say that if I'm combining 3 objects with spin half, I can get these guys. You don't have to keep track of the rules here. But there is a way that we can combine 3 spin half particles to get an overall effect of 1/2. And that's what we see in the proton and neutron. All right. Are either of these stable? Is a neutron stable? No. What do neutrons decay into? A neutron left to itself will decay into a proton, right? So obvious, right? So there's only one quark combination out there that's stable. It's the proton. Okay, the proton is the only stable particle. Neutrons are not stable. Neutrons decay into protons.
Why do they talk about proton decay?
You hear about proton decay all the time because it's never been observed, and theorists love the idea of proton decay. But it's been predicted now since at least 1960, and we've run hundreds of experiments looking for proton decay, and it's never been observed. And when it is observed, it'll be big news. We'll hear about it. But the other thing you hear about from theoretical particle physics, things like supersymmetry, right? String theory, all that stuff, we really have no experimental evidence for any of that currently. But one of the things that theorists keep saying, keep looking for this, those protons have got to decay. So we run experiments that show that the lifetime of a proton is, the numbers now are like 10 to the 40th years or something. It's amazingly long. We just don't see any evidence that protons decay. But again, that can change, right? It just takes one set of observations to turn that around. All right. Questions on any of this? So that's our list of matter particles. The leptons and the quarks. And let's see, where are the familiar ones again? We've been working with this one, we've worked with this one, and we've been working with protons and neutrons, which are actually combinations of quarks. Are there other combination of quarks out there? Yeah, there's like hundreds of different quark combinations. So let's look at a few of those.
I have a quick question.
Yeah.
Just going with the J side.
Yeah.
And I know you told the story, but how does that factor into the 3 generations?
What this was there was a search for the charm port, and the idea was how could we actually observe the charm port, because we don't observe these quarks individually. We observe them as part of other particles. So, in fact, that's kind of where we're headed now. What are the possible quark combinations that we do see? We don't see individual quarks coming out of a reaction. The possible quark combinations we see are what are called quark anti-quark. Okay, and that's what C bar is an example of. These are called mesons. And when the search was going on for the charm port, it was, theorized correctly that the lowest mass particle that contained a charm port would be something that would be C bar. That would be the easiest thing to look for. That's where we would start seeing these particles show up. So that's what people were searching for. And that's an example of Q bar, where Q is a quark. And anything that's in the form of Q bar is called a meson. Let's see, we've talked about a few of these, right? Do you guys remember the pi pluses and pi minuses in a couple problems? Pion decay. This is up anti-D. This is anti-up D, for example. So those are examples of mesons. Those are the lowest mass mesons. And then there's two other combinations of quarks that we see in nature. We see quark combinations. These are called baryons. And then we see anti-quark, anti-quark, anti-quark. These are called anti-baryons. But that's all we see. We don't see individual quarks. We don't see combinations of 4, 5, or 6 quarks. It's always quark, anti-quark, quark, 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 quark. And so the idea was, well, what's going on here? Why do we only see these quark combinations? And theorists came up with an idea of, okay, here's what's going on. There is a property of quarks. Quarks have a new property, and they called it color. They said that quarks have some kind of a property to them, like electromagnetic charge. They say this property, we're going to make up a name for it, we'll call it color. And the idea was there are 3 different quantum states for color. Each quark can either be in the red state, or the green state, or the blue state. We're just making up names for this, right? Now the analogy here is, go back and think about spin. If I have an electron, how much spin does it have? 1/2. How many different states could it be in? Well, it could be in 2, right? There's a spin up and a spin down state. And I can only assign 1 electron to one state. If there's another electron that comes around, it's got to go into the other state. It's the same idea, except now there's 3 possibilities. So if I have quarks coming along, and the first quark goes into the red state, what happens to the next quark?
Goes in the green.
Well, it's got to go into the green or the blue state. So by the time I've accumulated 3 quarks together, what must be the case? They must each be in a different color state. And that's how the theorists came up with this. So they said, okay, one of these is red, one's green, and one's blue. And the only way you can get an attractive force holding the quarks together is to get what's called a color-neutral combination. A color-neutral combination of quarks will give us a stable particle. So why are these the only quarks combinations that we ever see, because these are the only ways we can get color neutral states. The possibilities for color neutral would be to place one of each of the quarks in the red, green, and blue state. That creates an overall attractive effect, and the quarks clump together and form a proton or a neutron or a heavy version of a proton or neutron. What's going on here? What are the colors for this quark anti-quark? And it's red and anti-red. Okay. So in addition to the colors, we end up introducing anti-colors. So the anti-quark is in an anti-red state. If I have 1 unit of anti-red and 1 unit of red, what's my net color? That's 0. That's also colorless. So we have to get something that has color neutral. There's no net color around. And these are the only combinations. If it's an anti-baryon, I have to have 1 quark in each of the anti-color states. Okay. Now there's math behind all this. So there's mathematics behind this that where this symmetry is built into the mathematics. And it says this is when I get an attractive force and this is when I don't. Now, the quarks, I guess we got to step. Any questions on that before we get on? So that's the idea. And I guess we were talking about stability. That's how this all came about. Are there any stable mesons in nature? Apparently not, because we haven't talked about any. We did do some problems with these pions, but that was pion decay. These guys aren't stable. Why are there no stable mesons? Because if I have a quark and an anti-quark, how many net quarks do I have? 0. And this can actually decay. We'll take a look at examples. So something that is quark, anti-quark, definitely can undergo decay. So no stable mesons in nature. How many stable baryons do we have? 1. That would be what? It's either the proton or the neutron. It can't be both. Actually, it could be both, but it turns out it's not. It's just the proton. Proton's the only stable baryon we know of. What about anti-baryons? Well, the antiproton is stable. As long as what? As long as it doesn't encounter a proton. Okay. So isolated, antiprotons would also be stable. But that's it. That's the only. So the only thing stable here are 1, possibly more generations of neutrinos, the electron and the proton. And that's it. And the photon. Photons are going to be stable also, but we haven't gotten to it yet. Okay. Let's do a quick diagram. I'm going to go back and revisit. You guys remember beta decay? Okay. What happens in beta decay? Let's say it's beta minus. Let's use a familiar process. Carbon-14, that beta minus decays. How did we diagram that? We said, well, what was going on here is that the underlying reaction is a neutron turning into a proton, an electron, and a neutrino. What we're left with is nitrogen-14. The high energy particles coming out were the electron and the neutrino. Now, is this an anti-neutrino or a plain old neutrino?
Anti.
And it has to be the anti-Y.
Because it's producing.
Because that's a particle. Right, and if I created the electron and the neutrino are examples of leptons. Leptons are conserved. Can I create 2 leptons from out of nothing? No. Can I create a lepton and an anti-lepton at the same time? That I can do. So this has to be a lepton-anti-lepton pair. And that guarantees us the neutrino coming out has got to be an anti-neutrino, and it's going to be electron flavored. Now, let's diagram what's going on here. I just had a neutron turn into a proton can I take that down to the level of quarks? Yeah, so what I can do is I can say a neutron is really 3 quarks, up, down, down. And at the end of the decay, what flavors of quarks do I have? Up, up, and a down. So one of these quarks change flavors. Which one? Well, one of them. So we'll just say that this one here, up, up, down. And this is now a proton. Something happened along one of the paths. And we're going to say it's right along this path here. Right at that point, the D turned into the up quark, it changed flavor. The quark changed flavor at that reaction. So there is a, this is actually an example of the weak force. We got to get the other forces up here. We'll do that. This is an example of the weak force. At the other end of that weak force is going to be another pair of particles. What are they? So we started by saying carbon-14 decays to nitrogen-14. And then we said, oh no, wait a minute. It's a neutron decaying into a proton. And now we're saying, oh wait, that's not it either. What's really happening? It's a quark changing flavor. One quark goes from the down state into the up state. That's the decay that takes place in beta minus. One quark in one of the neutrons inside that nucleus. All right, we've taken a pretty good look at the matter particles. We talked about those. I guess we really need to move on to the force particles, right? So what forces are there in nature? There's gravity, but we don't have a particle description of gravity. We expect there is one, but we don't have that yet. What are the other 3 forces that are out there? 4 forces, actually.
Strong force?
Yeah, there is the electromagnetic force. There is the strong force. There is the weak force. Any others? There's one more. There's gravity. So the other particle force is the Higgs force. So you guys heard about the Higgs being discovered a year or 2 back? We can talk about that a little bit. Anyway, let's think about kind of a timeline here. We said that the quark model was coming into place in the 60s and 70s. By the middle of the 70s, there was a very well-established theory about how quarks behave. We had not found the top quark yet, but that was found probably 15 years later. So it did take probably 10, 15 years until we found the last one here. Eventually, all of the leptons were discovered. So what the force side of the standard model said that there are 4 forces in nature. There's a 5th one, there's gravity. But at the particle level, we want to be able to describe the electromagnetic force, strong force, weak force. What particle makes up the electromagnetic force? When 2 objects attract each other or repel each other through the electromagnetic force. That's actually done with particles. And it's done with photons. And the symbol for photons is our symbol gamma. And so the electromagnetic force is all done with just one particle. It's the photon. We already know quite a few properties here. How much mass do the photons have? As far as we can tell, none. I mean, it could turn out that they do have a little tiny mass, but again, it's something we've measured really carefully. If they do have mass, it's really tiny. Photons also have a unit of spin to them. Okay, they've got energy, they've got momentum. Strong force, what's the strong force made of? Strong force The strong force is not, oops, wrong particles here. The strong force is not felt by the leptons. Leptons do not experience the strong force. Only the quarks experience the strong force. And strong force is based on color state. So any quark can be red, green, or blue, red, green, or blue. And the way the strong force works is, like we talked about, it's an attractive force as long as you're building up a combination of quarks that are color neutral, but it's not otherwise. And what's the kind of defining feature of the strong force? It's really strong, okay? And it's so strong that it doesn't leave isolated quarks anywhere. Quarks quickly get gobbled up, well, they don't get gobbled up. Quarks quickly, through the strong force, combine to form mesons and baryons. So we don't see any leftover quarks in nature. All the quarks have been combined into baryons and mesons. When we run particle experiments to take apart protons, we still don't see the individual quarks directly. So the quarks reconfigure themselves rapidly and form new baryons and mesons. We can tell from the way that we're interacting with the proton that there are 3 particles there. We can tell what the properties are, but we don't. There's no long-lived individual quarks in nature, and that's because the strong force is so strong. All right. The strong force is made out of what we call affectionately gluons. Yeah, it's from the word glue. And gluons, we use a little g to keep track of gluons. And that says we got to come over here and we got to think about this picture with this neutron. This neutron has an up, down, and a down quark. What's holding them together? Gluons. How many gluons are there in there? There's just a really large number. So we've got gluons going on all the time. If we go back and take a picture of our proton, here's our proton. How many quarks did we have? Quarks in the proton? 3. So up, up, down. What are their color states? Somebody's got to be red, somebody's got to be green, somebody's got to be blue. It doesn't matter which one. And what's holding everything together? It's the gluons. So gluons are being exchanged all the time. And that holds the quarks together very firmly, right? You can't take a proton apart very easily. Go to extreme measures to disassemble a proton. Okay, so gluons are around here all the time in these particles. There are 8 versions of gluons. And you can kind of account for how many gluons there are by taking a 3x3 matrix. And what you can do is, well, let's take a look here. Let's take a look at this neutron right here. And I'm going to start out by saying this up quark is in the red state, and this down quark is in the green state, and this down quark's in the blue state. What kind of a gluon is that right there? And it's a gluon that can take the up and the down quarks in red and green states and switch their color states. So it takes this red quark and pulls up this, it takes this red quark and puts it into the green state. And it takes this down quark and converts it into the red state. And we have exchange of color. Okay, what would that be similar to? Well, it's like having an electron in spin up and spin down state. What do we do with the electrons? We reverse their spins. Okay, so it's the same idea. Taking 2 quarks that are in 2 different color states, and at the same time the gluons are holding the quarks together, the colors switch. And that's what the math does in the description, is it says, hey, we're going to get an attractive force by switching the color states on these gluons. All right. So how many different gluons would we have? And at first it would seem that there's 9, because what we could have is we could have, well, let's try this. We could have a red anti-blue, something that switches red and blue. We could have something that's red anti-green. We could have something that's green anti-blue, or something that is, I guess I didn't want it there. We could have something that is blue anti-red and green anti-red, and something, what's this one going to be? This is my blue column. Blue anti-green and green anti-blue. And then we've got these diagonal members of my matrix. So this one would be, I've got something that's red anti-red, blue anti-blue, and green anti-green. But there's a problem with a gluon that's red anti-red or green anti-green or blue anti-blue. What's the problem? Yeah, they don't change the color of anything, right? These are already color neutral. So mathematically what we end up doing is taking these 3 and doing linear combinations. Now when we come up with a linear combination, one of those linear combinations will always be color neutral, but the other 2 won't. So we end up with 9 minus 1, and that's what gives us 8 different flavor combinations of gluons. Okay, so when you guys are in math classes, you're talking about different functions and which functions can form bases and how we can convert one basis into another basis. This is the math that gets used in describing these different quantum states. We can write down 9 possibilities here, and then we can look for linear combinations. So linear combinations will also mathematically serve the same purpose, and that's how we come up with the number of these. All right, the weak force. What particles make up the weak force? And they should be like weakons or something like that, right? But they don't actually have a name. Okay, there is a name for these. These are called weak gauge bosons, but that's not a name. Right, come on. So anyway, we're just going to call these W and Z, and that's the name they go by. So there's 3 different particles that make up the weak force. There are positively charged versions, negatively charged versions, and there is a neutral version of the weak force. So there's 3 possibilities there, and they're called the W's and the Z's. And Z means we're getting close to the end here, right? So this is what the standard model looked like, say, 1975. The W's and Z's had been predicted, they've been discovered. The taus and neutrinos have been predicted, they've been discovered. Additional quark flavors had been predicted. Everything had been found except the top. So there were kind of at that time 2 remaining particles left to be discovered. One was the top quark, and one was the Higgs boson. Okay. Now, why did we need a Higgs boson? Why did people even bother about this? Let's take a look at an example here. We'll come back to this 5th force. Let's look at some reactions that we might run with these fundamental particles. What if I run a reaction like this? This is an E plus and an E minus. Now this E plus and E minus, they don't run into each other and annihilate, become a bunch of photons. This E plus and E minus interact with each other, but then they keep moving on. So there's still an E plus, E minus that comes out. We run these reactions all the time. What would the diagram look like? And these are called Feynman diagrams. Watch for these on the Big Bang Theory. They're on the blackboard in the back a lot. Okay. Different Feynman diagram set up. Feynman diagram would look something like this. Let's see, I've got an E plus coming in, and here is the E plus leaving the reaction, and then here is an E minus coming in, and here's the E minus leaving the reaction. Now, if they came in going in these directions, but they leave going in these directions, what happened? Because, let's see, I got an electron coming in here, I got an anti-electron coming in like this. They come in the reaction like this, they interact and they leave like this. Do they leave with the same momentum they came in with? No, that's not possible if they're coming out of a different direction, right? So momentum would have to have been exchanged between these two. It's like back in 4A, we would have called this a collision, right? We would have said it's an elastic collision. Two objects run into each other. Energy is conserved, momentum is conserved, but the objects don't necessarily head out with the same energies and momentum they came in with. What we do know is this. If these guys come in with a combined amount of energy, how much energy will these have? That will be conserved. So the total energy here equals the total energy here. What about momentum? What if I have a certain amount of momentum to start here? I've got to have the same amount of momentum in the after picture. So who's going to get the momentum and the energy shuttled back and forth? And that's what the forces do. The force particles take certain amounts of energy and momentum from one particle and transfer it to the other particle. Okay, and that's their job description, right? If you apply it to be a force particle, what kind of questions would they ask you in the interview? They say, are you reliably able to transfer and conserve quantities of energy and momentum and angular momentum? And if you say, yes, I can do that, I can make sure none will get lost, all of the energy, momentum, and angular momentum will be accounted for at the end of the day, then you're hired, right? So what kind of force particles could we have in this reaction? Could it be a photon? You go, absolutely it could be a photon, because why? Yeah, photons are based on electromagnetic force, and that says anything up here that's non-zero can interact through a photon. So quarks can interact through photons, electrons can interact through photons. What about the neutrinos? No, the neutrinos don't. Okay, but the electrons do. So this could be a photon. Let's move on. What about the strong force? Could it be the strong force that is causing this reaction to take place? Why or why not? What kind of particles are we looking at?
Leptons.
Yeah, we're looking at leptons. So, not going to be the strong force, right? Strong force will have no effect on these electrons. So it's not strong. What about weak? Now, weak forces, again, can act on everything. There's a property called weak isospin that we're not going to go into. But all of the particles have what are called weak isospin, and that says they all interact with the weak force. So yeah, this could be a weak interaction. Now, would this be a W or a Z? The way we've got this written right now. It would have to be a Z, because why?
The chart is going.
Yeah, this is coming out, this went in positive and it came out positive. A W would have transferred a unit of charge. Okay, so this could be a photon or a Z. Here's another possibility. What if this goes in as an E plus, but it comes out as an E minus? And what if this one goes in as an E minus, but it comes out in E plus? Is there a force on our list that would allow for these electrons to change their charge?
W. Be W minus.
Yeah, I can't get it done with one, right? It looks like we're going to have what?
Oh.
Yeah, we'd have to transfer it twice. This would, this is not going to get this done. So I'm trying to think if there's other options of possibilities here. think of anything right now. This one I'm going to have to think about some more. All right, I'll cross it off for now. But we can certainly have the weak force or the electromagnetic force, okay, that is causing this reaction to take place. And that's what we do. We kind of step through the forces and ask which forces possibly could be causing this reaction to occur. Oh, the Higgs. We never got back to the Higgs, right. Okay. When we go through and we do all the predictions, we now have mathematical descriptions of how photons behave, how gluons behave, how W's and Z's behave. And if we run the calculations on those, on the different types of reactions, we can predict what the outcomes will be. We can predict how frequently different reactions will take place. There's one problem, and that is when we look at all the different ways that the reactions could take place, often we have a property called divergence. Guys, heard of divergence in any of your math classes? If I have a series and it diverges, what does that say about the series?
It's not a finite.
It's not well behaved. It's not the terms in the series are not getting smaller and smaller. Instead, they're doing what? Yeah, they're getting bigger and bigger, but they're staying kind of the same size. The same thing happens in particle physics. In fact, this is one of the applications of convergence and divergence. When you run these reactions and you do the math, you'll end up with a series of terms. And for some of those, they converge, and for others, they diverge. Now, convergence is great. Convergence is great. We calculate the number. It tells us what the reaction is going to do. How do we deal with divergence? And nobody was sure. Peter Higgs, back in 1965, 1970, found out that if there was one more particle in nature that all the other particles could interact with, he found a set of particles that would eliminate all the divergences. All of them. So that was pretty exciting, and it wasn't a particularly difficult set of properties. The particle here was just kind of a simple sort of particle, and people started looking for the Higgs boson. Now this was discovered when? 3 years ago? Yeah. So if you go from the beginning of the Standard Model, which was probably, by 1965, the Standard Model was on its way. And at that time, it was predicting the existence of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to say 10 particles. And one by one, particle physicists checked those off. Everyone was discovered that was in the Standard Model of particle physics. And a few years ago, the last one, the Higgs, was discovered, and the evidence right now is it really is it. It has the properties that we were looking for in the Higgs force. So it really, the Higgs is best thought of as an additional force. Behaves the same way the other forces behave. What you can have is couplings between the Higgs and other particles. Okay. So you add in diagrams, and they take out the divergences. Yeah.
For all of those force particles,
yeah,
are those what they mean by virtual particles?
Yeah, so a couple things we should say. All the force particles, first of all, are bosons, which doesn't sound like a compliment, right? But bosons are what? What are we saying with a boson? The spins are going to be 1. So this has a spin of 1, these have spin of 1, this has a spin of 1. This actually has a spin of 0, but it's still a boson. Okay, question again was what?
Are those all mean by virtual particles?
Oh, virtual, yeah. So virtual is this. Do we ever see that photon? No. So this photon is contained within the diagram itself. There's no way to observe it because it did all the only thing we observe is the amount of energy and momentum that was transferred back and forth. We don't directly observe this Z, those are called virtual. So anything that's not directly observable is called a virtual particle. These guys are called real particles. Now, it doesn't have to do with their focal lengths, but it's borrowing on the names virtual and real. Real is something that either went into the reaction or came out of the reaction. Virtuals are all these intermediate particles which we did not directly measure.
What about the Higgs?
The Higgs is, typically it's a virtual particle. So I don't know that we will, I don't know if we'll ever directly measure, I want to say no. I want to say that we will never directly measure it because it's always going to be between two of these vertices.
Have they measured any of the ones that
What we measure is this. So we don't measure the Higgs directly. What we measure is what it decays into. So like in this example, not this one. When we did this example, this was neutron decay, right? We don't directly measure the W. The W is a virtual particle. We know the properties of the W by taking the properties of the electron and neutrino, combining them together. So if I combine these together, it will tell me how much energy the W had, it'll tell me how much momentum it had, it'll tell me what the electromagnetic charge was, and it will tell me what the angular momentum was. So I can reconstruct the W by looking at the decay particles. But we don't directly observe the virtual particles.
How come in the Feynman diagram that you did of that first time you had the neutrino going towards the weak force?
I did. Okay, let me put that back in.
Back in time.
Mathematically, antiparticles and particles behave as the same particle going opposite directions in time. Now, that doesn't necessarily mean anything, but what it does say is this. It says that this neutrino and this electron are the same particle. Right? Because, let's go back. The properties are different because why? The W came in and carried off or brought in whatever properties are different. So let's say here's the neutrino coming in, it has no charge. What happens once it interacts with the W? The W says, here's 1 unit of electromagnetic charge, and turns it into an electron.
What if you had it in a strong electromagnetic field?
Strong force square.
A strong electromagnetic field.
Oh, an electromagnetic field. Strong electromagnetic fields are just photons. So that would bring in, if we had this taking place in a strong electromagnetic field, that means we could be bringing in photons from the surrounding materials. Okay. So we could have photons that come in and energy could be absorbed or energy could be transferred in or out. So in particle physics, this is reality. Reality comes down to a list of quark flavors, a list of lepton flavors, a list of the fundamental forces in the particles that make them up, and then a list of which reaction vertexes are possible. So each one of these reaction vertexes that we look at, there is a coupling constant. Now you guys know a couple of these. What's the coupling constant for gravity? When two objects interact gravitationally, what's the constant that describes that effect?
Gravitational constant.
Big G. Right? What is the constant, the coupling constant for electromagnetics?
Q.
It was K, right?
Okay.
So each one of these forces has a coupling constant to it, and we can trace it back to this diagram right here. So what Feynman did, and I think it's kind of amazing what he did, he took something that was mathematically so complex that only a handful of people understood what the heck they were doing. And he said, you know what? Each one of these can be written as a diagram. Each diagram has a certain mathematical factor that you put in, and then anybody can calculate it, right? You go to school and you study this for a quarter or a semester or something. We're not going to do these. But once you learn the rules for how these come together, you go, any graduate student can do this, right? You sit down, you do calculations of Feynman diagrams. So in some sense, reality comes down to what are the coupling constants here? How does this process couple? What are the coupling values here? And there's only a handful of those. You know, there's a short list of 10 or 12 different ways that particles can couple, and you go, that's it. That's all the things that can, ever happen in nature. It's built on those 10 or 12 different types of reaction. All right. Any questions on this? Make sure we're staying with our time. We got a few more minutes here. Let's see what else we can look at. Let's look at some other decay examples. That's what we should look at. So let's try some of these. Okay, and the things we need is this table right here, I guess. It's all right here. All this could be printed on a card that's really small and you can carry it around in your wallet. You would have all of reality in your wallet. All right, let's try two in particular. I want to do this. I'm going to do muon decay is my first example. There I got a muon. Is the muon stable? No. Either it's stable or it decays. So where did the muon show up? Right there. Okay, so the muon is right here. What could the muon decay into? Yeah, it seems like it could decay into an electron. Now, it turns out that when the quarks and leptons change flavor, they can't go horizontally. They have to go back and they have to go zigzag. So it can't directly turn into an electron. But what a muon can do is it can turn into its neutrino. So let's start with that. So the muon turns into a muon neutrino. What kind of an interaction would that be? What kind of force just took place? Was it electromagnetic? Well, it can't be electromagnetic because photons have no charge. It's got to be something that can remove the charge on the muon. It's got to be a W. The only thing here in our list that can change the charge of a particle is the weak force. So this must be a W. And there's a reaction vertex right there. And there's my W. Now the W is going to be a virtual particle. It's going to show up as two other particles. What are the possibilities? And we're limited here by the mass of the muon. If I'm going to decay, can I decay to something heavier? It's got to be lighter. There's only one pair of particles that the muon can decay into. What would it be? It's got to be the electron. That's the only thing lighter than the muon on our list. So at the other end of this W, this must be an electron and an anti-electron neutrino. Okay. So again, what we're doing is we're following conservation laws. We're saying that, well, let's just do some counting here. How many leptons went into the reaction? One. So I have one lepton going in. How many leptons are coming out of the reaction?
3, 2, 6.
Well, I've got a lepton here. I got a lepton here. What's this? That's an anti-lepton. So what we're going to do is say +2 minus 1 anti-lepton. And that says my net number of leptons is going to be 1. So how did we do? Did we conserve the leptons? Go, yeah, the leptons got conserved. Now I can already see that in the diagram because why? How can I look at the diagram and say, yes, we've accounted for all the leptons? Because the force particles are drawn with solid lines. Right? So I can follow where the muon end up. The muon became the neutrino. So I can always have a particle in and a particle coming out. That considers the particle. How am I dealing with this right here? Well, this was a particle-antiparticle pair. So I can think of this as an anti-neutrino going back in time. And at this point, it picked up charge and properties, so it became an electron and started going forward in time. And that's +1, and that's -1. And that says this effect was no net lepton. Okay, question? Yeah.
If we were to do a tau on, whatever it's called,
solve decay, would you just kind of like add to the top of that?
Yeah, so I could do this. So what happens in particle physics is typically once you get one of these figured out, there's like 100 other reactions that look exactly the same, or at least some. So I could do this. Let's turn this into a tau instead of a muon. What's going to change on the other side?
Tau neutrino.
Well, this is probably not going to be a muon neutrino anymore. What's it going to be? It's going to be a tau because the most likely decay would be to stay within a generation. So this would probably become a tau neutrino. This is certainly one of the possibilities. With a tau, I've got more mass. Would these particles have to be an electron and a neutrino? What else could they be? They could certainly be a muon. So it could also be that this is a muon, and this is a muon, anti-muon neutrino. That's certainly a possibility. Does a tau have enough mass? It can produce this pair, it can produce it, it's going to produce this pair. And you guys don't know, right? Because we haven't looked at the numbers. Turns out a tau does have enough mass. It can also produce combinations of up and down. Okay. So this could either be an electron and neutrino, this could be a muon and a neutrino, or it could be something like an anti-up, and it's got to be minus, huh? And a down. Okay, that could also come out from a tau decay. So a tau's got options, right? It's heavier. There's many combinations of lighter particles it can turn. Ooh, and that's it. We better stop right there. So that's the idea. Solid lines for the conserved particles, dashed lines for the vertical, dashed lines for the force particles.